Hi there, my name is Bill Halliday and I'm an Associate Conservation Scientist with Wildlife Conservation Society Canada. Today I'm going to speak with you about a study that I led titled A Quantitative Soundscape Analysis of the Canadian Arctic between 2014 and 2019. Listed at the bottom of the slide are the many co-authors who were involved with the study. They either provided data or were involved in the analysis in somehow. So without them, this study would simply not have been possible. So a huge shout out to all of those people for making this work happen. The Arctic is changing. Climate change is happening at an increased rate within the Arctic, and when we think about underwater sound levels and the marine environment in general, we think about sea ice. Climate change is causing sea ice to decrease in many ways, whether we're talking about sea ice extent, thickness, or even the amount of multi-year ice versus first-year ice. All of these things are decreasing. The figure on the bottom left really depicts it well. This compares September ice extent in 1984 versus 2012. In 1984, you can see that sea ice covered the central Arctic and also extended down to the North American coastline and partially to the Russian coastline. Move over to 2012, it's entirely within the middle of the Arctic Ocean, touching Greenland and the Canadian Arctic archipelago, but not making it to the mainland coast at all. This is allowing for increased access for ship traffic. Ships don't have to worry as much about sea ice anymore, so they can travel more freely throughout the Arctic. They don't need to be escorted by an icebreaker or have a thickened hull. If we look at total ship traffic through the Canadian Arctic, for example, this figure on the top right, we can see that ships traveled a relatively consistent amount of distance in the 1990s, and even in the early 2000s, but then come 2005, there's a sharp increase in ship traffic. And a more recent report written by the Protection of the Arctic Marine Environment Working Group of the Arctic Council, or PAME, has shown an increase between 2012 and 2019 in ship traffic. Why are ships coming to the Arctic? Well, it's not just increased access, it's why they're accessing it. So a shipping route between the Pacific and the Atlantic, or the Pacific and Europe, so that would be the Northwest Passage or the Northern Sea Route, respectively. Natural resource extraction, whether that be oil and gas development or mines trying to ship their goods using the water. And then finally, tourist activity. This map on the bottom right shows the track of the Crystal Serenity, a large cruise ship that traveled the Northwest Passage, first of its kind, from Anchorage all the way to New York City through a route through the Canadian Arctic. The Arctic is considered an apocalyptic destination. Come see the Arctic before it disappears. Come see the Arctic before the animals are no longer able to use the sea ice. It's drawing a lot of people to the Arctic. With this increased ship traffic, we're assuming that there is increased underwater noise levels. Why wouldn't there be? More ships, more underwater noise. Now, there are a significant number of gaps in our understanding, though, for underwater noise in the Arctic. There was a recent report written by PAME called Underwater Noise in the Arctic, a State of Knowledge report. Myself and a couple of my colleagues were the authors on this study. We found significant geographic gaps in published studies on underwater sound levels across the Arctic. Within the Canadian Arctic, for example, there are just a handful of studies, most of which were in the Western Canadian Arctic, with only a single study in the east, nothing in the middle. So lots of areas to be filled in. Other gaps, the entire Russian coast, for example, we didn't find any published studies. And there are many other areas that have had no published studies or very few published studies. And effectively, this means that we don't even know what the natural variability is in underwater sound levels across the Arctic, simply because there are many areas that we haven't measured. Also, ship noise. How much is it contributing to the soundscape across the Arctic? What are the main drivers of variation caused by ship noise? So there are these gaps that we need to fill. And this study was trying to fill part of those gaps. So specifically focusing on the Canadian Arctic, I searched out collaborators, colleagues that had acoustic data, passive acoustic data collected across the Canadian Arctic. I found a total of 39 data sets collected from across 15 sites between the years 2014 and 2019. These sites are all shown by the dots up on the map, and the colors of those dots denote how much data has been collected at each site, between blue sites that are 72 to 90 days, so up to 3 months of data collection, all the way to red sites which have 3 or more years of data collection at those sites. Deployments, individual data sets range from a single month to a full year. The recorders were either duty cycled, they were either continuous recording or to an even extreme duty cycle of 1 minute of data recorded every 2 hours. Sampling rates were all greater than 1 kilohertz, but most of them were greater than 24 kilohertz. Recorder types, there were 5 different makes of acoustic recorders: wildlife acoustics units, ocean instruments, ocean sonics, multi-electronic, or units made by Scripps Institution of Oceanography. So a bit of variability in the type of data that was collected, but overall lots of usable data to compare. For specific methodologies, myself or my collaborators calculated sound pressure levels, or SPL, in 3 frequency bands, 50 to 1000 hertz, or 1/3 octaves centered on 63 and 250 hertz. Those 3 bandwidths were specifically chosen. The 50 to 1000 hertz bandwidth, the 50 hertz represents the lower sensitivity limit for wildlife acoustics units, and that makes up more than 1/3 of the acoustic recorders in the data sets, so a pretty important lower limit. And then 1000 hertz allows 38 of the 39 data sets to be included within that bandwidth. The 3rd octaves were both chosen because 63 hertz and 250 hertz are both used for analyses of shift noise frequently. 63 hertz is also mentioned in the European Union's proposed underwater noise guidelines. With those data, I calculated daily mean sound pressure level. I obtained daily averages of environmental data from Environment and Climate Change Canada data sets, specifically wind speed and air temperature. I obtained ice concentration, sea ice concentration data from the AMSR2 satellite and extracted the pixel values directly above the acoustic recorders. And finally, I estimated the number of ships within 10 kilometers of the recorders based on satellite automatic identification system data. I conducted a detailed statistical analysis on the data using mixed effect general additive models with the dependent variable of daily mean sound pressure level in each frequency band. Fixed effects were wind speed, air temperature, ice concentration, number of ships, the site or the water depth, as well as interactions between those environmental variables. And then all models included a random effect of deployment ID, which accounted for the variability among the 39 data sets. I also examined the influence of daily averaging on the results, as well as examining standard error around the daily mean values to look at variability amongst the sites. And I collated different metrics of underwater noise for each recording site based on different proposed metrics, as well as ones that I came up with on my own. Digging into the results, looking at the environmental variables specifically. So the columns up on this graph are for ice concentration, wind speed, air temperature, and depth. And then the rows represent the different frequency bands, 50 to 1000 hertz on the top, and then 63 hertz in the middle, and 250 hertz on the bottom. Across all these bandwidths, ice concentration always had a negative effect on sound pressure level. Under solid ice, sound pressure levels were lower than under ice-free conditions. Wind speed had a positive effect on sound pressure level. It was very windy. Ambient sound levels are typically high. Air temperature had a negative effect on sound pressure level, and then water depth also had a negative effect on sound pressure level. There were some important interactions that also need to be considered between ice concentration and wind speed, for example. At solid ice, so high ice concentration, wind speed had a reduced effect, effectively because wind wasn't able to interact with the water surface as much under solid ice, so it wasn't able to create as much underwater noise. Also an interaction between ice concentration and air temperature. Under solid ice, when air temperature changes rapidly, specifically when it cools off, that can create a lot of ice noise, which then increases sound pressure level. Trends were relatively consistent across the frequency bands, except for a couple of those interaction terms, and then water depth was only significant in the 50 to 1000 hertz band, but not in the other 2 bands. When we look at SPL by ships, as the number of ships increases within a day, so does sound pressure level. And then looking at seasonal patterns within variation across months, the open water season, August to October, had higher sound pressure levels than the ice-covered season. Lowest sound pressure levels were seen in typically February, March, and April. When we look at SPL across sites, there's quite a bit of variability between those sites. Sites that were more exposed to the open ocean typically had higher sound pressure levels than sites that were, say, contained within a narrow inlet with limited access to the open ocean. This can be shown between our MI site up on the screen, that's Minto Inlet, versus Baffin Bay 4, which is fully exposed to Baffin Bay. There are also frequency-dependent trends. Sites that have high levels, say in the low frequency band, don't necessarily have high levels in the 250 hertz band. I won't go into those specific site-wide differences right now, but we did find quite a few differences. Now looking at the effect of the daily averaging on results, as well as variability caused by daily averaging. So in one analysis, I took a single data set and examined SPL in 5-minute averages, and then again in 1-day averages, just like in the rest of the analysis. And I found similar trends. An increased SPL as wind speed increases with a similar effect size, and then a decreased SPL as ice concentration increases, again with a similar effect size. Looking at standard error around the mean, as you can see in this graph here, most sites are fairly similar. There are 2 sites that stand out. One is Gascoyne Inlet, GI, up on that figure. This site had the most extreme duty cycle, 1 minute of data recorded every 120 minutes. And that site, you see high amount of variability. So that site had effectively the least amount of data in that daily mean. So the most chance for there to be high variability from one 2-hour period to the next 2-hour period. Pond Inlet was the site with the highest amount of ship traffic, and effectively, more ship passages means more variability within that day. Finally, getting into my metrics of underwater noise. The first metric was looking at mean daily sound pressure level greater than 100 decibels. This is a metric that was proposed by the European Union, specifically in the 63 hertz band, but I do look at it in all 3 bands. So how often was 100 decibels exceeded within a day? In the 50 to 1,000 hertz bands, all sites had at least some days above this threshold, some sites more than others. In both the 63 hertz and 250 hertz bands, 11 sites had some days above this threshold. Now, I will note that trends in this specific metric don't seem to be related to anthropogenic activity. Looking at mean daily sound pressure level greater than 120 decibels. 120 decibels is the behavioral disturbance threshold by NOAA. It's specifically targeted at a shorter time period, but even still, it's a useful comparison point. The only bandwidth with sound pressure levels greater than 120 decibels was the 50 to 1,000 hertz bandwidth. And only 6 sites had 1 or 2 days above this threshold. And it didn't seem to be related to ship traffic either. Finally, a metric that is related to ship traffic. Ship traffic, number of ships per day in August, October. Only 1 site had greater than 1 ship per day on average. This was at Pond Inlet, and this was the site that measured all the ship traffic from the Baffinland iron ore mine, which tends to be causing increases in ship traffic within this region. So that site had relatively heavy ship traffic. 6 sites in total had greater than 0.2 ships per day, or 1 ship every 5 days. And these sites were related to proximity to shipping corridors or a destination for cruise ships. And then the remaining 9 ships had less than 1 ship every week, effectively, throughout the shipping season. So just wrapping up, some projects for future research: a better quantification of ship noise, what is causing variability in ship noise, what types of ships are causing the most noise, what environments seem to allow the most propagation of ship noise, do faster ships cause more noise, these sorts of questions. What are the source levels of ships traveling in the Arctic is also an important question. Filling in other geographic gaps within the Canadian Arctic, for example, gaps that we did not fill, the Kitikmeot region, so in the central Canadian Arctic around Victoria Island, east and south of Victoria Island, the high Arctic or last ice area up in the Arctic archipelago, above the shipping, effectively north of the shipping lane. And then finally, Fox Basin, Hudson Bay, and Hudson Strait. We don't have any acoustic recorders from those regions, and those are regions where we need more data. They are regions with a bit more, especially Hudson Strait, does tend to have ship traffic in more parts of the year than other areas of the Arctic. So it's an important area to be monitoring underwater sound levels. And finally, just thinking about which metrics and targets of underwater noise are best. Our results looking at either the 100 decibel or 120 decibel effectively, all sites, almost all sites anyway, surpass the 100 decibel threshold. So is it really that useful of a threshold? Whereas the 120 decibel threshold didn't seem to be related to shift traffic. So again, is it a useful threshold? So we need to think about this. And with that, I will thank many, many partners and organizations involved in the study, the communities and our community partners at different communities in the Arctic, research vessels and crews aboard those research vessels, funding from many different organizations, as well as other data contributors. And with that, thank you.